Hello, Calculus 1 student. Finally, let us begin calculus. Lesson 2, Limit and Continuity. All calculus begins with limit. And let's approach in 3 different directions. First is the easiest, the graphical approach. Here are a couple of motivational examples. Here's an interesting graph, and please note that there are some interesting points. Here, x equal to -84, and right there, x equal to 3. And then we have some asymptotes here, horizontal and vertical asymptotes. Those kind of things are related to limits. What is a limit? Limit is a value that the function value gets closer and closer and closer to. So it's a real number, yes. Excuse me, I take it back. It's an extended real number. It could be infinity. In any case, the function value gets closer and closer there as the x coordinate. The number in the domain gets closer and closer to whatever. And we express like this. Well, it's really hard to understand. So let's go back to the graph again. Let's go to x equal to -84 here. The function value is right here, y coordinate. Y coordinate clearly is 3. Do you see that? Y coordinate. Look at my mouse here, and I'm pointing toward the dot here, and that's part of the graph, and function value is y coordinate. But this is a function value, not a limit. Limit is right here at y equals to 1, because if you get closer and closer to -4 in terms of x coordinate, either from the right or to the left, the y coordinate will get closer and closer to 1, either from right hand side or from the left hand side. So the limit and function value are not always the same. Right here at x equal to -84, they're different. And then at x equal to 3, again, they're different. Function value here, you can see the dot, I hope. Function value is 1. That's the y coordinate value. Now, if I approach from the left, x equal to 3, from the left, I'm following the graph from the left, and that's getting closer and closer to which y coordinate? 2. Y coordinate 2 this way. From the right, y coordinate is getting closer and closer to -1. Do you see that? So from the right hand side, the function value gets closer and closer to -1, this y coordinate value, from the right, and then from the left hand side, follow the graph, and you can see f of x gets closer and closer to +2. Now, if you look at the function value on the other hand, f of 3 is, what is f of 3? What's the y coordinate? This dot. You see, in this case, they're all different. We see something similar here. From the right, we follow the graph. From the left, we follow the graph. And either way, in this case, we get to the same y coordinate value. F of x approaches to y coordinate value 1. Right here, either way, from the left or from the right. And the function value at -4, well, that's 3, right here. So the limit behavior, which track down the graph and moving around or use the arrow, and the function value, which is basically a dot, that behavior are not always the same. You see, function value here, function value there. And that's when x equals to -4 here, and that's when x is going to +3 there. And for any other x coordinate, no problem there. Whatever point here, function value, which is a point on this graph, y coordinate here, -0.7 or whatever, whether I follow from the right or left, they're all the same. No change here, no change there, no difference here, no difference there. Most of the points, no problem. And there are two x coordinate values, they have some difficulty. -4, that's one of them, and then +3, that's another. Let's elaborate this idea a little bit further using the left and right hand side limit notation. So we use these kind of notations. Axis approaching to C, do you see this negative sign here? This one is left hand side approaching, and this one here is right hand side approaching. Do you see this C minus here and C plus there? In mathematics, positive is right hand side direction, negative is left hand side direction. And the y coordinate value as I follow the graph from the left hand side and the y coordinate value as I follow the graph from the right hand side need not be the same. Let's see. Okay, is there any good way to put those into the same viewing window? Let's go ahead and copy and paste it here. Okay, and then let's bring back those arrows again. So green, following the graph from the left hand side. Green, following the graph from the left hand side. Red, following the graph from the right hand side. Following the graph from the right hand side. See the difference? And C plus here versus C minus here. That's how we represent one-sided limit. From the left-hand side limit, the right-hand side limit. Some people call it positive side versus negative side. C minus, albeit less than C, so left-hand side. C plus, a little bit bigger than C, so right-hand side. And look at the color coding in the graph. Approaching from the right-hand side, red, plus side. Approaching from the left-hand side, green, minus side. And those y coordinates do not always have to be the same. At x equal to 3, they are different. This y coordinate, +2. This y coordinate, -1. At x equals to -4, they happen to be the same. Those y coordinates are both +1, but the function value is somewhere else. And all other x coordinate values, the function value, limit value, left hand side, right hand side, they're all the same. Those kind of points are called continuous points. And then these kind of exceptional cases, those are called discontinuous points. And let's elaborate that idea. So the function value, and then the left-hand side limit, and the right-hand side limit are all the same, then we say a function is continuous there. And if the left-hand side limit and right-hand side limit are the same, then we use just limit notation without plus or minus, you see? So left-hand side expression and the right-hand side expression. See the difference? Limit c minus, limit c plus. If those are the same, then we use the limit notation without plus or minus. Just limit x is going to c. So we have basically 4 different expressions. The limit expression, where left-hand side and right-hand side put together, and that makes sense when left-hand side and right-hand side limit are the same. And then of course we have left-hand side limit, right-hand side limit. And finally the function value, the original y-coordinate value. In algebra classes, we never cared about the limits. When we look for the function value, we just found out the x-coordinate and then went for the part of the graph. Whether it's a dot or a solid curve, doesn't matter. Just went for that particular y-coordinate. So we used to consider only f of c only. In calculus now, x is moving a little bit. X does not stay constantly at c. It moves around c. The closer the better. And then whether it is approaching to c from the left-hand side, as highlighted in green, or from the right-hand side, as highlighted in red. They can be different. Sometimes they are the same. And then when they're the same, we use this limit without this plus-minus expression. So pay attention to these expressions. And then let's go back to, sorry about that. And then let's go back to the motivation example again. I'd like to get those arrows back. Okay, these kind of things. Left-hand side limit. And then those kind of things. Right-hand side limit. And then the function value. Function value, those are not very good. I didn't want to erase everything. Never mind. I think we went through the same picture often enough. Okay, let's go back to an exercise problem set. Okay, let's go ahead and exercise here. Wait a minute, it's the same graph. Okay, alright. Stop the playback and answer all these questions. f of -4, the left-hand side limit, the right-hand side limit, and put those together. So what's this? Blue. And what's this? Green. And what's this? Red. And what is this? Purple. And then do the same for x equal to 3. So f of 3, the function value, and the left-hand side limit, the right-hand side limit, and the limit without specifying. Okay, what do you get? Well, here are the answers. All good? Function value is +3, right here. And then the left-hand side, right-hand side limit are all the same y-coordinate here. So this limit expression is well defined, and that's a common value of 1. Now, for the next problem, it's the other way around. Function value is 1 right here. And from the left-hand side, going to 2, that y-coordinate. From the right-hand side, going to -1. And then these two are different. So this limit is undefined. It does not exist. Finally, determine all x-coordinate in which f is discontinuous. Well, x equals -4 and +3, otherwise all continuous. So you can express in the interval expression like this. And check back to your picture. Does it make sense? Continuity versus, the common idea of continuity versus the limit expression.